very well-known device researcher, and personally, I read so many papers of this group, and many papers defining their field, very important contributions to electronics. And he's the founding director of the NanoHub. Many of us actually go there on a daily basis. And he has been elected to U.S. Academy of Engineering and as well as many other honors. So it's my pleasure to introduce Mark to give the next lecture along for the right on reflections of past, present, and future of computational electronics. Let's thank you.
Thank you. I don't know, is this microphone working?
Is it? I'm not sure. No, it's on.
It's on, yeah.
Is it on?
Delayed for 7 seconds.
Okay. All right. Well, thank you, Hung. So I really appreciate the invitation to be here and to speak. I should let you know this talk will be completely different from the first talk. There will be very little science. And thank you for indulging me. You know, I think we're at a transition period in electronics. People talk about the end of Moore's Law, whether or not that will happen, we can debate. It'd be interesting to hear. We have people from Intel and IBM here. But things are changing for sure. And computational electronics, this is a workshop about modeling and simulation. Modeling, simulation, computational electronics has been an enormous part of the success of this story. So it's a good time to reflect on what we've accomplished and what the future might be. A lot of graduate students are asking these questions. Is this a good field to get into? What are the next 40 or 50 years going to be like? So this kind of talk, is occurring frequently at workshops and conferences that I'm going to. Usually it's in the evening, where people serve a lot of beer. The audience is feeling very good, and they're willing to challenge the speaker. And I'll encourage you to think of yourselves as having had several beers. You're in a good mood. You don't agree with everything that I'm about to say, so you don't need to wait until the end. We can have a discussion through this. So I'll count on some of you to help keep the discussion going. Okay, so I've been very fortunate to have been in this field for a while, and so the title sort of says that, why isn't this working? But what I would like to do is just reflect on where we've been and where we're going. Okay. All right, so, pardon me? Not working? All right. Oh, now it works. Okay. All right, this is where it started. The invention of the transistor, 40 years before I was born. As people have pointed out, if you look at that device, it would have been hard to predict that it had a bright future. Looks like a bent paper clip here. This is a piece of germanium. You can see why it's called the base, because it holds everything. But we've come a long ways, and this is the smartphone. So this is the quinfinitesimal device that defines 21st century electronics. More and more, devices like this are going to drive the future. The next 20, 30, 40 years are all going to be about mobile electronics. The technology that gets created are going to be driven by needs for mobile electronics. And the big question is, what is 21st century electronics? Are we going to hit an end of silicon electronics and have to switch to radically new technologies? Or what's going to happen? This is on everyone's mind. So this is what I plan on doing. I'm going to give you a very brief view of the role that modeling and simulation played in all of this from my own perspective. So, then try to draw some just observations and lessons that we might learn from that. I'll talk a little bit about nanotransistors. Usually when I'm giving presentations today, this is about a 1-hour seminar on the physics of how these very small devices operate and how small we can make them. But I'm going to do it very, very quickly. And then speculate a little bit on where we're heading. So I hope it'll encourage you to think about this, debate with me, and maybe we can have some good discussions during the talk and after the breaks. Okay, so transistors were invented. You know, when they were first invented, they were intended to replace the vacuum tubes, but they weren't very good devices. I remember a colleague told me a story from John Bardeen when we went to Illinois. Somebody asked him, you know, these new devices, these transistors, what are they good for? You know, they're fragile, they can't take very much power, they don't work at high frequencies. They're really not the device to replace vacuum tubes. And his response was, yes, you know, it's not really a very good device, but there may be certain niche applications that it could do. Hearing, I think he mentioned hearing aids. But that was very important. They found something early on that the transistor could do that the vacuum tubes couldn't do. You could create a business, you could generate profit, you could fund research, you could create new technology, you could expand the market, and when you do that for 50 years, it has a lot of impact. This is one of the first applications. And this was actually built 60 miles from where I now work, in Indianapolis, Indiana. This was the first, notice it's called a shirt pocket radio. It looks a little too big to fit in a shirt pocket. But it was an early application of something that transistors could do. You wouldn't carry around a vacuum tube portable radio. It really became big with Sony when they introduced their 6-transistor shirt pocket radio in 1957. I understand that this also was a little too big for a shirt pocket. But Sony had specially made shirts for his salesmen that had pockets that were just a little bit bigger so that they could slip the transistor radio in. And, you know, things started to take off. But it wasn't obvious. When I was a kid, I would tinker with radios and I would read these ham radio magazines. There was a lot of discussion and debate about where are things going. It wasn't clear that transistors were going to take over. And I remember reading a few ads like this. So this is one from RCA talking about how they weren't standing still. They could make vacuum tubes very small. And they were in the race with the transistor industry to see who could build the best electronic devices. But things began to happen very quickly at about that time. And in fact, there were a few individuals that recognized that the whole future is semiconductor electronics. But there was a problem at that time. All electrical engineers were being taught vacuum tube electronics. The future was semiconductor electronics. The only books were probably Shockley's Electrons and Holes and Semiconductors, some notes that Bell Labs used to have short courses on transistors. There really wasn't a set of textbooks that you could use to teach engineering students a technology that was going to be the future. So a group of people got together. They produced a set of 6 paperback books. They called it Seek Notes. I was still using these when I went to college, a couple of them. And they made a few movies too. And they very quickly enabled people to be able to teach semiconductor electronics. And all over the country and all over the world, engineering students started to learn semiconductors instead of vacuum tubes. When I took my first electronics course at the University of Minnesota, it was probably 1971, the transition was complete. I remember my professor came in one day and he said, "You're electrical engineers, you should know what a vacuum tube is." And he gave us one lecture on vacuum tubes. So things happened very quickly. I graduated with my master's degree in 1974. I went to work for Hewlett-Packard. So semiconductor tech, this was very sophisticated, state-of-the-art technology at that time. The first process that was, whoops. I think I'm back where I want to be. Yep. So the particular plant I worked at was located in Colorado. The first N-channel MOS process had 7-micron feature sizes, 7,000 nanometers. I joined and worked on a 5-micron process. This was incredibly small for the time. You know, if you go ahead and read the Hewlett-Packard Journal about this, this was called a shallow junction technology. They were 2 microns deep. That was shallow junctions. The gate oxide, today they're less than 2 nanometers, almost 1 nanometer. They were 100 nanometers. And I remember my group leader saying, gate oxides will never be less than 1,000 angstroms. It's not possible to do that. We were learning all kinds of stuff for the first time. It was really hard to make 5-micron channel lengths work because we didn't understand short channel effects. The famous paper was written the year we were working on this. I had to become a metallurgist. I didn't realize if you put pure aluminum on silicon and heat it up to center the contact, it alloys right through in shorts. We had a 5-volt power supply because everything we did had to be compatible with emitter-coupled logic, which was the main technology. We had a 6 megahertz clock, which was really fast for the time. And we were building 16-bit microprocessors years before they were available on the open market. In fact, what we were doing in our division was we were building desktop computers and selling them to engineers. Years before the IBM PC, and before Steve Jobs. We didn't realize that there was a market for desktop computers. We were just selling them to a few other engineers. Okay, so that was great fun. One of the things I started to do as we were doing the process development is I would see these PhD theses come along from universities. I would read papers, and people were beginning to simulate the performance of transistors. And they were solving these things we call the semiconductor equations. So the Poisson equation and 2 continuity equations for electrons and holes. And then we had the various constitutive relations, and we described current, its drift plus diffusion. So this was a coupled set of nonlinear differential equations that was really challenging to solve at the time. I remember reading these. It was interesting to read them. They weren't very much used to me at all in what I was doing and struggling with the challenges I was trying to struggle with in order to make this process work. But I sort of filed that away in the back of my mind. That's really interesting. If you looked at the models that we used, the models were simple analytical models that were then later developed into SPICE models that could be used for circuit design. And they were expressions like this, the square law theory of the MOSFET. If you go back and read these papers, it's just amazing how good of device physicists these people were. These days, when I investigate a novel device, I usually first do a detailed simulation. I understand what's going on. I try to express it in a simple way. They didn't have detailed physical simulations. But it's amazing how much they got right, how much has stood the test of time. So they were really outstanding. So things you started with. This is the paper. So this is a famous paper by Bob Bernard of IBM, published in 1974, the year that I started working on this 5-micron process. Reading this paper, suddenly everything became clear. We knew why we were having so much trouble making these 5-micron channel lengths work. It was all because of 2-dimensional electrostatics. And Bernard and his colleagues really laid out very clearly, very simply, what this was all about in a paper that had great impact. So one of the things you learn is that, 1,500 citations. Citation counts are really not always a good measure of impact. The impact that this paper has had is just enormous. The whole industry now knew how to scale devices, and for the next 40 years, that's what they did. Now, if you read this paper, you can see that he read some of the early papers on full numerical simulation of transistors. He got insight and understanding. Now, I remember reading papers by Mach, not nearly as many citations. There was a smaller group of people that were reading this, but Bernard and his colleagues were able to take that, to distill the essential concepts, to present it in a way that everybody working in this field could read it and understand what it was all about, and the rest is history. So there was actually quite a lot of work done in trying to solve these devices. Most of these names are probably lost to the younger people in the audience, but I remember them all. I see J.G. remembers a few of these too. Herman Gummel at Bell Labs was the first one to come up with a scheme for solving these 3 coupled nonlinear differential equations. and that was really challenging to do. He and Don Scharfeder then learned how to discretize the equations. One of the troubles we had early on is that you would get things like negative concentrations of electrons if you didn't understand how to discretize the equations properly. They did beautiful work on that. People started doing complete two-dimensional simulations of transistors. First bipolar transistors, because that was the main technology, then MOSFETs. And there was a number of work, but this work didn't have great impact in the field, at least not yet. Where the impact really started to happen in terms of really changing the way device R&D and manufacturing was done was when people like Siegfried Selvaher came along and wrote a two-dimensional MOS simulation program that solved those semiconductor equations, but made it free. It was designed to run on a mini computer, a VAX, I think, at that time, and it was freely distributed. Anybody could get a copy. And suddenly everybody started doing device simulation, and it became a tool that people doing process development, like I was doing, could begin to use for their own problems. This isn't such a seminal paper, but I include it to show you what I was doing at the time. We were learning how to include compositionally non-uniform materials in these simulations. An awful lot of this work was done by seat-of-the-pants engineers, people without a lot of mathematical and numerical analysis training. They had a problem to solve. They needed to learn how to solve these equations and get the job done. It is really amazing what they were able to do. But then later on, people, this work was done at Bell Labs with Bank and Rose and Wolfgang Fichtner. Mathematicians were brought into it. The numerical methods got very sound, very efficient. Ways to make the equations converge under almost all conditions were developed. And the codes really got very much more robust and much more useful. Here's another paper. This is another program that had tremendous impact. This was a two-dimensional Poisson and continuity equation solver written by Mark Pinto and his colleagues at Stanford. There isn't even a paper. I couldn't find a paper on this, but it had enormous impact. They wrote it and they gave it away. This is one of the most widely used device simulation programs that was, early on that was out there and that people began to use. So that idea of giving away the software so that others can be able to map out carrier densities and electrostatic potentials and things like this had enormous impact. Okay, so then you could take those tools and you could go back and you could do a better job that Denard did. You could really do the device scaling in a much better way, much more rigorous. This is a study of device scaling that was done at Bell Labs with some outstanding people. And this is showing how the junction depth, oxide thicknesses, depletion depths around the source and the drain regions are all related to the minimum channel length. They came up with an empirical law that did this. So this paper also got a lot of attention. But it didn't get nearly the attention that simple Denard paper did, because Denard encapsulated the basic ideas in such a simple and clear way that everyone working in the field could understand what you needed to do, and then you would go to this detailed simulation when you really needed to do that. Okay, so we had these powerful drift diffusion simulators that could solve these equations, and one of the things that kept happening over the years, devices kept getting smaller and smaller, and the physics kept getting more and more complicated, and one had to go to more and more sophisticated numerical methods to capture that. So one of the things that became important was to be able, high fields, carriers moving, hot carriers, the classic drift diffusion equations would begin to break down, so people started solving hydrodynamic type equations. And there were a lot of interesting problems that came about due to that. So here's an example of something that we were working at this time. Mark Spetler is in the audience, so Mark is now at Intel and is going to give us his perspective on where TCAD stands at Intel right now. This particular problem we were looking at the assumptions that are made when you create a hydrodynamic or energy transport model to try to do a little better than drift diffusion. And all I want to show you here is there's a model device structure. This is a source, this is a drain, this is a channel. It's a simple 1D NIN structure. And what we're looking at in the red line is the computed heat current, temperature times the entropy current. These were solutions. We had learned how to solve the Boltzmann equation, at least in one dimension. So we could look at things very rigorously from a semi-classical point of view. And we were interested in heat flow and energy transport. The electrons are moving from the source to the drain, so they're going to carry heat from the source to the drain. So you can see a positive heat current flowing, and then it increasing due to this scattering in the channel where you get a lot more heat and temperature, and then dropping down in the drain. Now, what was interesting to us is that if you look at most classic derivations of hydrodynamic flow equations, there will be various moments. One of the moments is identified as the heat current, and it involves something called a peculiar velocity, which is the deviation from the velocity from its average value. You look at this moment and you say that looks like heat. It's the random component of the energy. And it's called heat. It's called Q in these energy transport models. So we could go ahead and we could calculate this moment. And the interesting thing that we discovered that would surprise us a bit was that, first of all, it wasn't the heat. It's not the same temperature times entropy current as heat. It's quite different. In fact, it has the wrong sign. Here's zero. I mean, if electrons are flowing from the source to the drain, they should be carrying heat from the source to the drain. And yet this quantity in the hydrodynamic models that you call heat had the wrong sign. Easy to see when you look at the quantity. So there was an enormous amount of work in this time period to try to improve the drift diffusion models by doing hydrodynamic type simulations. But one of the things we began to appreciate is all of the approximations that need to be made. If you worked very hard, you could make it work for a specific device at a specific voltage. But you were always worried, what if I change my device structure? Or what if I operate it at a different voltage? Do all of these assumptions that I'm making work anymore? And what that sort of led to is that there is relatively little use of these equations anymore. And it's because people just don't know whether they can believe them or not. So one of the things that really surprised us, the very first mathematical description of semiconductors, the drift diffusion equation with the Poisson, is still probably the most used technique in semiconductor R&D. Because you know what its limitations are, you know when it breaks down, you know which parts of it you can't believe, and when you need to go better, you skip over this and you go to much more refined techniques. And those were Monte Carlo simulations. So people began to do these in the 60s, actually. So these were, you would trace the path, the trajectory of an electron through a semiconductor as it underwent a random walk, scattered, was accelerated by the fields, scattered again. People first began looking at them to try to understand the velocity versus electric field characteristics in materials like gallium arsenide, where you get unusual velocity field characteristics. Later on, as semiconductor devices began to get smaller and smaller and the supply voltages were not scaled initially, reliability problems became very important. And you had to worry about very energetic carriers and what was going on with carriers that were very high in the bands. So people took these Monte Carlo simulations and they began to add to them a full numerical description of the energy band structure and began to do things like impact ionization and the injection of electrons into the oxide. And it became a very useful tool for understanding those. And then the group at IBM really took that work that was originally done at Illinois and extended it into a very sophisticated simulation capability to simulate semi-classical carrier transport in semiconductor devices. So we had the ability then, semi-classically, to track electrons through the entire Brillouin zone in K-space and in real space at the same time. And this became the technique when you wanted the most accuracy. But semiconductor technology just continues to march forward.
devices get smaller and smaller and smaller, and then you start to worry about quantum mechanics. And you worry about how do we use quantum mechanics in our simulations. So some of the first work from a device perspective that I'm familiar with is the work by Supriyo Datta and his students at Purdue when he started applying the non-equilibrium Green's function approach, or Keldysh method, to semiconductor devices. At that time, the device of interest, the quantum device of interest, was a resonant tunneling diode. Then at Texas Instruments, a group of people developed what is really the first TCAD, the first actual R&D CAD tool that comprehended quantum mechanics. And that was developed by Lake and Clement Bowen and Jovanovic and their colleagues, and it was really focused on transport through resonant tunneling devices. And this work now has become very sophisticated. So the current version, NEMO 5, is a full quantum mechanical treatment of a small semiconductor device, including both elastic and dissipative quantum transport. It's become an industrial strength code being used by companies now to look at ultimate CMOS and at devices beyond CMOS. What you're seeing here is an example of a tunneling device. You'll probably hear more about this later on from Suma and others. So you're seeing here electrons tunneling from the valence band of the source. A gate voltage pushes the conduction band in the channel down, and the interband tunnel from the source to the valence band of the source into the conduction band of the drain. And you can get some improved operations at very low voltages with schemes like this. And we now have the tools that we can look at these kinds of capabilities. Okay, so and then one more part of the story on quantum transport. As we were trying to understand transport in transistors, molecular electronics came along. And a group of people began to look at how do we understand current flow through single individual molecules. Now, one of the first teams that did that was a team at Purdue led by Supriyo Datta. I include this because it's interesting. Supriyo is a theorist. This was an experimental project. We need to see more of that, those of us that do computational. I mean, the time came, you could only go so far with theory, you need to do the experiments. I believe some of the first measurements on the conductance of a molecule were done at Purdue by this team, led by Supriyo. But in the process of doing that, they learned how you think about transport through single molecules, how you simulate it, how you extend these Green's functions approaches. And then others, including Hung Go and his collaborators, have really refined this to a very high level. And we can now do first principles, atom by atom simulations of electronic devices. So when you look at what's happened over here, when I look at it from my own perspective, in reading these theses that were coming out of universities in the mid-1970s and see where we were standing there, and then have been part of this and watching my colleagues do others, and you look at what's been accomplished over this 40-year period, it's really amazing. The effort of an enormous number of people over an enormous time period. But the programs and the tools just became more and more powerful, more and more sophisticated, always driven very much by the needs of the research and the manufacturing communities. So we can now do first principles simulations, either a DFT or tight binding. We still do drift diffusion coupled with Poisson as the main workhorse. We can do full solutions of the Boltzmann equation with Monte Carlo techniques when we need more rigor. And we can do full quantum approaches. No one technique, the difficulty is no one technique can handle any one problem. This sometimes bothers students. Can't we just put all the physics in one code and you'll get the right answer? So this is what makes it interesting, I think, for those of us that are studying problems by computation. You have to put together the right tools. You have to know which parts you can believe, which parts you can't. They get better and better all the time, but it's hard to see where that we'll have a capability anytime soon to put everything in and be able to trust the answers. So what comes out of this is insight, understanding, and also some new directions for research. And it's had enormous impact. So I'll label them in this way. So one of the things it's done, we'd really like to see more of this, but there are a number of examples where people who do theory and simulation have identified promising avenues for research in novel devices, and subsequent experimental work has been undertaken. So that's a way to have impact. We'd like to have more of that. Another way that it's had impact is to broadly communicate insights and understanding. So one of the things that's happened over the course of all of this work is we've had a set of conferences developed that are devoted to modeling and simulation. And these have been enormously helpful in terms of helping the community discuss methods, refine their techniques, push the progress forward. But there's a downside to that also, that communities can begin to talk to themselves and not communicate to those outside. And really, everything that we're doing here is to impact experiments, manufacturing, device technology. Dennard had the ability to take what was going on in the computational community, to understand it and present it in a way that the entire community could understand it and act upon it. So if you can communicate the insights from the simulation in a way that people who aren't computational experts can understand what it's all about, it has great impact. The other thing that had enormous impact is when people begin to share their tools with the community, to give them away open source. The prime example was SPICE for circuit simulation. But quickly after that, or a few years after that, the same thing started to happen in device and process simulation. And that really magnified the impact of those tools greatly. Okay, so that's my own particular view of been involved in some of this, watching it go on for a while. I'm sure if somebody else presented this, you'd have something of a different flavor. And there's an opportunity to hear about that. I'd like to. But I'd like to talk for just a few minutes now about just some observations and lessons learned. So Leo Kadanoff is an excellent physicist, and he's written over the past several years some articles about what it means to do good research in modeling and simulation. And he points out that if you write a computer simulation, you should be doing it for a good reason. And he identifies 3 good reasons. So one is to explore uncharted territory. And we've seen some examples of this. You have an idea for a novel device. You think you have a tool that captures the essential physics. You can see whether that idea has a chance to work on that. A second is to pose a well-solved scientific, to resolve a well-posed question. And we've seen examples of that. Much of the early work that we did was driven by problems. How do you understand why, when you scale devices down, their characteristics degrade? We learned how to, Dennard learned how to solve that problem. Many of the first programs were written because there were problems with things like CMOS latch-up. There would be a 4-layer switching device that gets built unintentionally when you do a CMOS technology, and it can switch and short the circuit out. So there were people that were looking at well-resolved problems. And the last is to make a good design choice. And in the process of all of this work, we've developed really powerful CAD capabilities. Really, people can't do their work these days without doing computer simulation. And you look at experimentalists, I noticed, talking with some of Suman's students, just using CAD tools is just a routine part of what we do. When I did MOS process development a long time ago, there were no CAD tools. Now you can't do it without those. If you're interested in just this general topic of what makes modeling and simulation effective, you can see his talk on these subjects on the NanoHub. And we actually had a whole workshop devoted to this topic, excellence in computer simulation. You can hear a lot of people give their opinions about this. So a lot of the work that got done over the past 40 years was really done by people that had problems to solve. They weren't computational experts. They might have been experimentalists. They had a problem, and in order to solve it, they had to write a simulation program. But later on, experts in more of the underlying physics and chemistry and numerical analysis made absolutely critical contributions that turned those initial codes into the tools that we all use. And I like that when I think about this, I like to think about there are different kinds of individuals that participate in this work. There's a group of people that are very close to the problem. They're interested in building a new device, in understanding a phenomenon that's limiting the performance of a device. They wrote many of the first versions of these tools. There's another group of people that are very good at the underlying details of the physics, at the mathematical and numerical methods, and they made the CAD tools as powerful as they are now. There are very few people that can do both ends of the spectrum. There are a few, but there aren't very many. So we have to work together. We have people who work at this end of the spectrum need to have important problems driving their work. People at this end of the spectrum need the sophisticated physics and numerical techniques in order to be able to solve the problems that they're interested in. And you could think of these two different types of people as the analysts, people who like to analyze problems and write sophisticated codes to do that, and experimentalists or designers, people who are building things and want to understand what their experiments are telling them or need to design something. And I think it's interesting. There's an interesting book here written by a fellow who's now passed away called Engineering in the Mind's Eye, which is really an interesting book to read. And he talks in this about an example. There was a bridge that was built in Canada, and it fell down. It collapsed. And they traced the problem to a CAD tool. He was on this particular person writing this was on a commission that was investigating why did this happen, what do we do to make sure that it doesn't happen again. And there was a finite element program that was used to design the bridge. There was some problem in it. Now you might have expected him to blame the people who wrote the program and say we need better quality control, you have to work harder on that. But that's not what he did. So he pointed out that when you use sophisticated CAD tools like this, and all fields of science and engineering now do that, the entire profession is going to rely on tools that are written by a small community of people. Right? It's just they're so sophisticated, they're developed over so many years. That's the way it has to be. And those people are the analysts. They're not the designers or the builders. So the analysts have to understand that there is no way that they can fully appreciate everything that goes into the experiment or to the product the way that people who are building bridges or chips can. They don't have the same kind of knowledge and day-to-day experience going in the lab, seeing what's happening. They'll put in the program what they're familiar with and what they're able to solve given the limitations of the hardware and the algorithms. So their experience is limited. But his point in writing this report is that the designers are going to do this, and we need to develop designers that understand that the tools will always be limited. They'll be the best that we can do at this particular time. Sometimes nobody even knows what's inside these tools. They've been developed over so many years by so many different people who have added so many different things to the code. No single person understands everything that's in it or what it does. So his point was that designers have to develop the ability to be able to not to rely on it and blame it if it gives them the wrong answer, but to be able to understand what it's giving and to be able to reject it based on their experience. They know that this result can't be right. It's the person who used the program. It's their responsibility to make that decision. So he has this phrase, stand up to a computer. We need to teach people who use sophisticated CAD tools to stand up to a computer. And I see this, probably all of us who teach. You have a new student who uses one of these programs for the very first time. They run the simulation. They bring you the results. You ask them, well, how do you know this is right? And you think, well, it has to be right. There's this company that's selling it for millions of dollars. It's been used for 30 years. It couldn't possibly be wrong. And it takes a while to explain to them that it can. This is another paper that I like by my colleague Konstantin Belucha, who spent many years doing TCAD at National Semiconductor. And he talks about the different people who use these tools come into two categories. The first is the category that you don't want to be in. The person who just says, well, the program has nice, sophisticated output, it has fancy graphics, we had great short courses on how to use it, it costs a lot of money, you know, it must be true, I'll just run it and take the results. But he's arguing that, well, the true technology developer is someone that doesn't necessarily believe the results that come up. They know how to check it to make sure that they're getting the right answer. So one of the challenges that I have is a student will come in and bring a result in and show me, and I'll say, well, why does it do that? You know, how do we know it's right? And it's hard. Students are losing the ability to be able to check the results. Because the first generation of people that wrote these, they were weaned on pencil and paper and back of the envelope. They knew how to do this. It takes a while to instill in a student the ability, how do you check the results and know whether you can believe it or not? Oftentimes I'll find students I'll say, well, why does this occur? And you say, well, in this part of the program, you know, you go from this statement to that statement, and there's this for loop. No, I don't want to know what the program, I want to know physically, why does it do this? So the true technology developer will do that. It's not something that's easy to learn. It takes, like Constantine says, it takes years of training and practice. You can't get it with short courses. It doesn't matter how sophisticated and nice the tool is. It's just something that it takes a while to learn. But that's our responsibility if we're training students in this field. Here's a picture that I got from Constantine. This is a colleague of his at National Semiconductor, probably retired now. He's a very famous analog circuit designer. And the title of this was His Computer Lied to Him. He knew that the results that he was getting from his CAD tool were not right. That's okay. You know, I don't believe it. You know, I'll find another way to get the answer. But you know, he knew how to check his results, and he knew when to believe them. And that's what you have to do. Okay, and since, you know, sort of, I told you this was going to be a different kind of talk. So what I want to share with you now is, I don't know if some of you might have seen this before. You know, this is a reviewer's comments that I got early on in my career, which caused me to think about what I was doing. Fortunately, they weren't reviewing my paper. Right? This is one of, you know, they review a paper and they share all the comments from the others with you so you can see what others did. But this one could have been written about one of my papers at that stage. And I read it and I did some thinking. So this was a paper. It was a paper written by a top group in our field. Okay, so the reviewer says, you know, as is the nature of this kind of simulation, I don't know why you put simulation in quotes, but almost nothing is explained. One must believe that with the right techniques, the curves come out as they do. A few features can be explained, but for the rest of it, all the reader can do is gaze at the plots. He wants to understand something, but he's not. And he was a very thoughtful review. He said, I'm not trying to put these people down. I realize they're one of the top groups in the world at what they do. But the point he was making is that they're talking to themselves. They're talking to other computational experts. I'm not a computational expert. I want to understand something from this. They're not talking to me. Okay. So he goes on. He talks about the references, lots on simulation techniques. He says there's no way you can really understand what they did in this paper because it would take at least 60 pages to explain all of the techniques, and you can't write a 60-page paper. So you just have to sort of believe that they did it right. And another point he makes here, which I think is a good point, is that they don't connect. They don't bother, they don't even try to connect their results to simpler analytical results, to the kinds of ways that people outside of the field do their work. They don't relate to traditional or simplified approaches. They just show you the results of sophisticated simulations and say, here's the answer. Okay, so then he gets to the point where you have to decide, tell the editor whether this paper should be published or not. So he says, well, could this be altered to make it more accessible? He says, probably not. The nature of this type of thing says, unless you are able to give the entire code away so that I can see what you did, There's no way to explain it. It's just too complicated. So this, I told you, one of the things that caused me to think about my own work is when I write papers to try to explain it to people who have no interest in modeling and simulation, but they want to understand the answer to the problem. So that comment caused me to think about that. This comment started me to start thinking, if I write a paper on a simulation technique, I'm going to give the code away. You can see exactly what I did. Right? I'm going to look at it. Here's his final conclusion, which is kind of pessimistic. He sort of throws up his hands, there's nothing I can do, this is the way it's done. And I started thinking that's not the way it has to be done. We can change that. Okay, so so here's one way that you can do modeling and simulation. This is for a person who's close to the problem, that's what I am. I started out as a process development engineer. I ended up getting involved in simulation. I always thought of myself as an experimentalist with a computer. Nobody who's really a serious computational person thinks of me as a computational scientist. People who aren't sometimes call me one, but they don't know what they're talking about. But here's an approach if you're interested in using computers to solve problems. So usually it's a good idea to start with a simple analytical model, like the people who developed the first SPICE models that we're still using. Based on what you think you know, can you describe it simply, the essence of the problem? These days, I would include a simple MATLAB model as it's almost an analytical model. You write a little MATLAB script to do it. Okay. Now that'll guide you in terms of the experiments you have to do, in terms of the detailed simulations. Unless you have some idea of what it is you're looking for, you don't know what simulations to do, you don't know what experiments to do. That'll help you refine the model. Okay. But now you're not done yet, because you're not done unless you can take the next step and communicate what you've learned in the result of all of this to people who don't know anything about modeling and simulation, but want to understand what problem you solve. And then you should share the codes so that everybody can see. If anybody has any question about what you've done, exactly how you implemented your scattering or your self-energies or your boundary conditions, they can do that. Okay, so let's move on. All right, so I'll have a little bit, I'm going to give you an example of some work that I was involved in for about a decade. And this is the part of the talk. Usually I give about an hour technical seminar in this. I'm going to hit the highlights, but I'm going to talk about nanotransistors just as an example of modeling and simulation. So if I look back to where we were in the late 1990s, I wish I could find the citation for this. I don't remember where I got this. But we were seeing this all the time. We were seeing plots like this that, here's Moore's law, here's feature size, here's the number of transistors. These were probably on a memory chip. We were down here in the late 1990s. We were getting channel lengths that were beginning, I think they were about 250 nanometers. We thought we might be able to get to 100 nanometers. And it looked almost impossible to get further. Okay. And I remember, the end of Moore's law has been predicted many times. And I remember talking with my friends and colleagues at this time, in industry at this time, saying, yes, you've said this before, but it's never been true. And the answer was basically, yes, Mark, but this time it's different. There are just a whole array of issues, economic, technical, it's all coming together. It's going to be really, really hard to get below 100 nanometers this time. At the same time, we had the birth of molecular electronics. Bill Clinton announced his National Nanotechnology Initiative, with his mission to build 1,000 Pentiums on a grain of sand with molecular electronics. And there were really, a lot of people thought this was, Moore's law is going to end. We are going to need to go to technologies like that. That's the only way to keep scaling going. Now, at the same time, we had learned an awful lot about the physics of MOSFETs. These are some Monte Carlo simulations that were done by the IBM group. And some of the things that we were learning or thought we were learning were, first of all, far from equilibrium transport is important. So what you see here is the bottom of the conduction band under high drain bias. Each dot represents an electron. You can see that we're very far from equilibrium. The electrons are way above the bottom of the band. They're streaming quasi-ballistically across the channel. This particular simulation in 1992 was of a 30 nanometer channel length, which I remember thinking was just silly. No one would ever make a 30 nanometer channel length. But it was clear that we were a long ways from equilibrium. Concepts like mobility in bulk semiconductors near equilibrium were not relevant at all. We need the whole band structure. Quantum mechanics was becoming important. And these authors say so, but something was happening. You know, I would go to conferences and I would hear what experimentalists were taking from this. And one statement I heard from one of my colleagues who was an experimentalist who said, these devices have become so complicated you can't understand them. All you can do is run a simulation and that's the answer. Now, that disturbed me. I mean, how do you know what experiment to do? How do you know what simulation to run if it's so complicated you can't understand it? So we thought, thinking, is it really that complicated? Can we understand it? We and several other people then began to look at this. I should back up here again. Yeah, you know, I organized a workshop in 1998 where I had a whole bunch of people together. There was a lot of pessimism there. But one of the things that I realized on that was that this was just too important. No amount of effort was going to be spared to keep this going. And suddenly, you know, I realized that these devices are going to be pushed to the smallest possible dimensions. They are probably going to be the smallest electronic devices manufactured. What about molecular electronics? So I really began to feel that the importance of molecular electronics was as a vehicle for understanding the science of current flow in very small structures. And that would help us push silicon technology to its limits. So we tried to see, you know, where are those limits? So we did things, whoops, I'm going the wrong direction. So we did things like solve the ballistic Boltzmann equation. So here we're just showing some results where we're resolving the distribution function along from the source to the drain of a ballistic MOSFET. So you're seeing these ballistic peaks and everything. We understood semi-classical transport. We began to use NEGF simulation techniques. And here I felt I could go to my colleagues who were studying molecular electronics. They had tools and techniques. They were able to understand measured characteristics of extremely small devices. They had techniques to simulate them and get sensible answers. So we felt we could look from 250 nanometers. We could look out to 10 nanometers. And we could do it with techniques that we had some confidence that we're going to get reasonable projections. So we began to use these techniques. What you're seeing here is the local density of states in a ballistic MOSFET. And here we've filled up those states with electrons streaming from the source to the drain. This is what happens when you turn on scattering. You wash out all those interferences in the local density of states, and now you have electrons at all energies. But we felt we could use those tools to look ahead and see whether silicon transistors could be scaled. These were some simulations that we were a little more sophisticated. Instead of looking at simple structures where electrons came in from the source through some magic contact, we could have a 3D contact, a 2D channel. We could look at how those electrons squeeze from a 3D contact into a 2D channel. Interesting things happen. Here's the local density of states. These are the so-called prime subbands. These come unprimed subbands. These come from the ellipsoids whose long axis is located along the degree of confinement. They have a heavy effective mass. So you see a lot of states in the contacts, and you see a few states in the device. If you look at the unprimed, those that have their ellipsoids oriented in the other direction, so they have a light effective mass, their energies are pushed up, you'll see that a lot of those states are populated in the contacts, but there are none of those states in the channel because their energies have been pushed so high. So one of the things that we've learned is that this is a case where scattering helped you. That unless you had a lot of scattering in the source and the drain, you couldn't get those electrons from the higher states to filter down into the lower states where they could access the channel. And the performance actually increased when you turned scattering on in the source drain. Okay, so we had a lot of those simulations. One of the things that those simulations showed us that conventional MOSFETs continue to behave in very classical ways all the way down to 10 nanometers and below. You could continue to shrink these and the device was still going to operate as a good transistor. But we also spent a lot of time in trying to learn how can we understand what we learned through all of those detailed simulations. So one way to think about that is in terms of energy band diagrams. So here's my silicon MOSFET. Here's the N-type source, P-type channel, the N-type drain. Here's the gate oxide, here's the gate electrode. And if we look at the electron energy versus position along the top interface, it'll look something like this under equilibrium. So N-type source, Fermi level above the conduction band, N-type drain, P-type channel, Fermi levels way below the conduction band. So this is what it looks like under equilibrium, or low gate voltage, no voltage applied to the drain or the source. So the device is off, the electrons in the source have a big energy barrier that can't flow to the drain. But potential energy is minus Q times potential. You apply a voltage on the gate, increase the gate potential. Well, let's see. Before I do that, let's increase the drain potential. So we apply a voltage on the drain, we pull the energy in the drain down, but if we haven't applied the potential on the gate, the barrier is still there and this device is still off. Now apply the voltage on the gate, push the barrier on the gate down. Now electrons can hop over that barrier and they can flow from the source to the drain, and we've got a transistor switched on. That's really all there is to a transistor. That's how a transistor works. You just have potential energy barriers that you have to manipulate with an applied voltage, and you make a transistor that way. So we can understand the operation of a MOSFET just by controlling these potential energy barriers, and it gives you a very simple physical picture, and that's really all there is. The main thing in transistor design is designing the electrostatics so that you can manipulate these energy barriers properly. All of the transport that I spent my career working on at many of them, drift diffusion, hydrodynamic, Monte Carlo quantum, that's less important. What's important is how you manipulate the energy barriers. So it's electrostatics plus transport. The reason we're going to more sophisticated structures now, like these FinFETs, is simply to try to wrap the gate around the channel so that we can hold that potential barrier up when we apply a drain voltage, and that way we don't pull the potential barrier down. The barrier height is controlled more by the gate than by the drain potential. So it's mostly electrostatics. So then we went back and looked. If you will look at 90% or more of the textbooks still being used, and if you would ask, my guess is 90, not the device people maybe, but the circuit designers. Most circuit designers still think of a MOSFET the way they learn in a textbook. And it's like this. So here's a simple MOSFET. If you look at this low voltage regime, you say current is the width of the MOSFET that's coming out of the page times charge times velocity. Okay. Current is continuous, so I can evaluate it anywhere. If I evaluate it at the beginning of the channel, it's just the gate capacitance times the threshold voltage minus the voltage it takes to turn it on and make a channel. Okay. The velocity is just mobility times electric field. The electric field is just the drain voltage, the voltage between the drain and the source divided by the channel length. Put that all together, and we've got the textbook description of the IV characteristic for low drain to source voltage. Okay. Now, if you want to do that for high drain to source voltage, we have to be a little more careful, because we know that when the carriers get hot, the mobility degrades, and it's been known for a long, long time that if you measure the drift velocity of electrons in silicon, once the electric field gets above about 10 to the 4th volts per centimeter, the velocity saturates at about 10 to the 7th centimeters per second. Because their increased energy causes increased scattering, the velocity just saturates. Okay, so we can't use velocity as mobility times the electric field. It's the saturated velocity. And if you put numbers in for a typical MOSFET for these days, you can see that these electric fields are about 500,000 kilovolts per centimeter. We're way above the electric field it takes to saturate them. Okay, that makes it even, that's going to make it even easier, but there's one problem. Everything we understand about transport says that that won't happen in a small device. So if I look at these Monte Carlo simulations, and if you simply plot the average velocity versus position, just go to any position, add up all of these electrons, and compute their average velocity, plot their average velocity versus position along the channel, you can see that the electric field is highest near the drain. That's where you'd expect the velocity to saturate. But if you look at that profile, you can see that there's no hint that it's saturating at the velocity that it saturates at in a volt semiconductor. So the velocity doesn't seem to saturate at all. Okay, but let's say, well, I'll point out one of the things people were talking about, people who were understanding transport started quoting the average velocity of electrons in the channel. And you started hearing people say, as I make my channels shorter and shorter, they're just going to get better and better because the electrons will go faster and faster. Okay. All right, let's assume that we didn't understand transport physics. Okay, that we understood textbook physics, that velocity is saturated. So I'll go back and I'll compute the IV characteristic. Current is width times charge times velocity. Charge is still Cox, Vg minus Vt. That's just MOS electrostatics. And the velocity now, it's even simpler. The velocity is just the saturated velocity, 10 to the 7th centimeters per second. Put that, we've got the classic velocity saturated model for the MOSFET, been in the textbook since late 70s, early 80s. And it explains why the velocity or why the current under high drain bias increases linearly as Vg minus Vt. Right? Looks like it explains everything. So everything works fine, except that we know physically it's completely wrong. Okay. So we have this textbook expression. If you look at the output characteristics and you see the current increasing linearly with gate voltage, an experimentalist will say, aha, that's the signature of velocity saturation. The velocity is saturated in these devices, and my model accounts for that. Okay. But we know that the physics is all wrong. Now, something interesting happens. This is a recent semi-empirical short channel MOSFET model in which they can take essentially that classic textbook model, and they show that it produces beautiful fits to IV characteristics for a whole wide variety of transistors. Silicon, 3.5. What we're seeing here, I think, are 32 nanometer channel length devices from Intel. There's a paper coming out in TED in a month or two that'll look at this in 20 nanometer. It still seems to work pretty well. And you can find, with only a few physical parameters, you get beautiful fits. You take that textbook model developed in the 60s and 70s, you fit it to modern day MOSFETs, it fits beautifully. You just have to do two things. You take the effective mobility that's been in the mobility of electrons in the inversion layer, and you replace it by something called the apparent mobility. You just adjust it a little bit. And you take the saturated velocity that we know is unphysical, and you replace it by something we call the injection velocity. And you find you can fit transistors beautifully, just with those two simple fits. Now the question is that just empirical, or is there something more to it? So the question is, why does this model developed in the 60s and the 70s, based on physics we know to be completely wrong, still describe modern day transistors so well? So there are two obvious answers. So my friend Colin McAndrew tells me, Mark, it's obvious. He says, these equations describe this functional form of an IV characteristic. This is what we call a transistor, a device that has an IV characteristic of this shape. Those equations describe IV characteristics of this shape. The last 40 years or more of device scaling have been about making the device smaller and smaller and preserving the shape of these IV characteristics. So those equations have to work, right? If we got some other shape, we wouldn't call it a transistor, right? And I say, okay, Colin, you're right, but I think there's more to it than that. I think those two parameters, the apparent mobility and the injection velocity, they're not empirical parameters. There's actually physics there. There's more to it than this. Okay. So how do we get at that physics? All right, we have all the simulations. Right? We know how the transistor works, but we want to understand it in a simple way. So this Landauer approach is very good for this. So we can think of the transistor as the channel being described by some number of channels and by some transmission coefficient that gives the probability that we'll go from the source to the drain. We think of the source and the drain as two Landauer contacts that are in thermodynamic equilibrium, well-defined Fermi levels, and we can describe it with this well-known formula. So this ought to apply. This ought to give us a sensible way to compute the IV characteristics of a MOSFET. Much more sensible than what we were doing before. Okay, I won't go through all the mathematics. It's actually not very difficult. But if we take this expression, and if we expand the difference in Fermi levels between the source and the drain for small voltage, then it's just proportional to the voltage. So this is the low voltage regime. We can evaluate this integral. The transmission is related to the beam-free path and the length of the channel. The number of channels is related to the band structure. Okay, we can easily evaluate those, work out the integral, and we'll get an answer. I'll show it to you in a minute. We can go to high drain bias. Under high drain bias, we apply a large voltage to the drain. We lower the Fermi level in the drain. So the Fermi function in the drain, the probability of states being occupied by the drain is basically 0. So F1 is much greater than F2. We get an even simpler integral to evaluate. Again, we know the number of channels, we know the transmission, we can work out that integral. Okay, if you do that, these are the answers that you get. As I said, it's really not difficult at all. You get an expression for the IV characteristic in the low VDS regime. Doesn't look anything at all of the textbook 60s version. You look at the expression at the high drain biases. It does look like a textbook expression, but instead of the high field saturation velocity, it's the thermal velocity of electrons coming out of the source, the thermal equilibrium velocity of electrons coming out of the source that's in there. That's what comes out of it. You plot the characteristics, they look just like a transistor, because the shape of those characteristics comes from manipulating energy barriers, not about transport, whether it's Landauer or drift diffusion or quantum. Okay. And this was first done by Notori in the mid-1990s. Okay, so we have a description of the ballistic MOSFET. If I want to put scattering in, I just multiply by transmission. It's a little more involved under high drain bias, and the reason that it's a little more involved is a little too long to get involved in right here, but it has to do with self-consistent MOS electrostatics. The key thing is MOS electrostatics. The charge at the beginning of the channel is Cox, Vg minus Vt, and in a well-designed MOSFET that holds all the time, and in order to make that happen, you come up with an expression that looks like this. Okay, so we have our Landauer theory of the MOSFET. Turns out that the transmission, there are several things we could talk about, but I don't have time to go through. But one of the interesting things is the transmission is much higher under high drain bias than it is under low. And that doesn't make, under high drain bias, you would think that the electrons have more energy, they scatter more, it should be less ballistic. And the reason that that occurs is something like this. Under low drain biases, the electrons have to go across the entire channel without the ones that don't scatter end up coming out the drain. You can write the transmission very simply. It's the mean free path over the mean free path plus the length of the channel. Now, under high drain bias, first of all, the thing to notice is that lambda naught means it's the near equilibrium mean free path. Low energy, near equilibrium carriers. there's this region near the beginning of the channel where the mean free path is near its equilibrium value, but it has just a very small thickness. If electrons can get across that, if they can transmit across that region, their probability of doing it is given by this. It's the length of that bottleneck, not the length of the entire channel. Then even if they get to the high field region and gain a lot of energy and scatter a lot, they're bound to come out to drain and contribute to steady state drain current. So the bottleneck is very short. So the device is less ballistic under high drain bias, but it operates closer to its ballistic limit because the scattering happens in a part of the device where it doesn't have much effect. Okay, but we're not done, because what we need to do is to take what we've understood and relate it back to the traditional view that most people who work on transistors continue to use. So how do we do that? Well, you take these expressions that don't look anything at all like the traditional view, but you remember that, well, transmission is related to mean free path. Mean free path is related to diffusion coefficient. Diffusion coefficient is related to mobility by the Einstein relation. So you just do a little bit of algebra and rewrite it. And what do you find? You find that the small drain bias current is given by the traditional expression, but instead of the real mobility, it's something called the apparent mobility. So this is not an empirical factor. It comes out, it's 1 over the actual mobility, 1 over the apparent mobility is 1 over the actual mobility plus 1 over the ballistic mobility. What's the ballistic mobility? It's the mobility that you would get if you replace the mean free path with the length of the channel. So when your device gets very short, it's the ballistic mobility that controls it. Okay. So there is some physics to that apparent mobility. If you do it under high drain bias, you can do the same thing. You can take this expression, you can relate transmission to mean free path to diffusion coefficient. And in this case, you'll find the current is capacitance, probably should be a width in there, times a velocity, and the velocity is 1 over this thermal injection velocity that they come out of the source, and 1 over V over L. V is a diffusion coefficient. L is the length of this bottleneck region across which they're diffusing. Diffusion is random thermal motion. Nothing can diffuse faster than the thermal velocity. So if your bottleneck region gets too short, this quantity will be bigger than the thermal velocity and will become insignificant, and you'll just approach the ballistic limit. So if we look at this, what we think of is the MOSFET. We have this bottleneck regime under high drain bias. The current is limited by carriers diffusing across that bottleneck. They can't diffuse faster than the ballistic velocity. This relationship makes sure that it does. This comes right out of the Landauer approach. This is also an empirical approach. You can go back to the 1970s and you can find people using this, because people could make bipolar transistors with very thin bases in the 1970s, and they were already worrying about ballistic transport, and they were using expressions like this to make sure that they got sensible results. So the MOSFET looks just like the bipolar transistor, as pointed out a long time ago, and a lot of the same considerations apply. Okay, so if we go back, some of the things I think that we learned is that, yes, there's a lot of far from equilibrium transport, but in a well-designed transistor, that's not what's controlling the drain current. The mobility is not irrelevant, because the mobility is a measure of the mean free path near equilibrium. And the bottleneck are these electrons here at the beginning of the source near equilibrium. The band structure, yes, you'd like to do the band structure, but you can get most of the essence of it without a detailed band structure, because most of the current is limited by electrons near the bottom of the band. The device, one of the things we learned by doing all of this with non-equilibrium Green's function simulations is that this device, the way it is designed, is inherently very classical. It's hard to see quantum effects, and when you see quantum effects, it's just tunneling and things that are easily understood. If we saw complicated quantum effects, we probably wouldn't have a transistor. We would have some other kind of device, and we would go back and redesign it until we got a transistor. Okay, and it's not too complicated to understand. It's really easy. In fact, so I'll tell you a little story. When I submitted the paper explaining this, I got back the reviews. And of course, you get the normal things. But there was one comment by one of the reviewers. He said, this is a nice little paper. There's only one problem. Any undergraduate could understand this. And my response is, that's exactly why you need to publish this paper. People are making it too complicated. All right. Now, there are a lot of details worth worrying about. And this was first done at 250 nanometer channel lengths. Now we're trying to figure out what happens at 10 nanometer. It will obviously break down, but we'll learn something in the process when we find out where does it break down and how does it break down. Now it's also, let me point out, now it's amazing that with a simple model like this, there are only, in this virtual source model developed at MIT, it's based on these concepts, there are only about 5 physical parameters. With those 5 physical parameters, you can model any well-behaved transistor of any type. And that's amazing. When you look at the detailed simulation, there's all kinds of complex things going on. But there's just 5 simple parameters. You can model any good transistor. And I was catching up on my reading on the plane out yesterday. And I read this paper in Science that was published just last month. It's called Parameter Space Compression Underlies Emergent Theories and Predictive Models. It's a very interesting paper. And they point out that, across many areas of science, you'll find that very complicated phenomena that's very complicated microscopically on the macroscopic behavior can be described with just a few simple parameters. They say problems tend to have a few stiff parameters that control their overall behavior, and a number, they call them sloppy parameters. This seems to be a technical term used in this field. A lot of details that really don't have a big impact in the overall performance of the device. Okay, where are we heading? Well, as you continue to scale down, problems occur. The biggest problem, I think, is still electrostatics. How do you maintain the control over these energy barriers the way you want them to be? But there are other problems. There are many other problems. So one is tunneling. So here's a simulation done by my colleague Mathieu Louisier. NEGF simulations. The blue is the energy band diagram from the source across the channel out the drain. The red band here is the energy resolved current. So it shows you for a 13 nanometer channel length, all of the current is flowing over the top of the barrier. Push the barrier down, more current flows. This is the way a transistor is supposed to work. If you go to 10 nanometers, still very classical. Still works the way a transistor works. You can see a little bit of tunneling underneath. You go to 7, you start to see a lot of tunneling underneath. You go to 4 nanometers, and the electrons almost don't see a barrier. All right, so this is a problem. As you're trying to modulate current flow by moving that barrier up and down, the performance is going to degrade. That doesn't mean that you can't do something about this. You can look for materials with heavier effective mass, for example. There are things that might be done. They're completely different transistor concepts. But it looks as though we can take the traditional silicon MOSFET, and if we can handle parasitics and electrostatics and all of the other things, we should be able to get below 10 nanometers. Right? Easy for me to say because I'm not a process development engineer at Intel, but I think we'll end up below 10 nanometers somewhere. Probably not 4. Now, the other thing that occurred during the development of all of this is that the techniques that were developed to understand ultimate CMOS also applied to all of the new devices that came along, nanowires, nanotubes, graphene, lithium disulfide, and everything. Now we had tools that allowed us to be able to treat those problems also. We were fortunate during that time period to work with Hongji Dai and Ali JB on carbon nanotubes. But there's a lot. This has now become a standard tool for looking at post-CMOS devices. Okay, so, putting this all together, molecular electronics came along. Bill Clinton gave his big speech. We were all excited about 1,000 pentiums on a grain of sand. Now, anyone, I think, who understood semiconductor technology knew that that didn't make much sense. right? That was not going to happen ever. You know? But you could see that this is a vehicle for understanding current flow at very small dimensions, and that is bound to be very useful. And I think it turned out to do that. We could use what we learned there to understand what the limits of CMOS were, and then we could use those tools and techniques in learning to be able to look at all kinds of novel devices which we're still doing today. Okay, so I don't. All right, good. All right, so here's the big question that I do not know the answer to, but we need to be thinking about this. What's the future? Okay, so we have this amazing electronics. It's getting better and better all the time. It just seems to be getting better, faster. And the question is, what's this going to be like in the future? If you're someone who likes to do theory and modeling and computation, where do you invest your time and energy? If you do technology development, where do you do that? This came from a presentation that we saw at the IEDM last week from a fellow at NVIDIA, whose name I have to find. But he had this little picture here, which I thought was a really good illustration. We're all talking about work down here. We have created an amazing technology that can be leveraged to do incredible things. Most of the world sees what's happening up here. These amazing products. It looks like science fiction, and just more and more is going to happen. There's just tremendous leverage in this technology that we've created. If we just stopped and went home and quit today, I don't know, 10, 20 years, most of the public might not even know that progress in the underlying technology has stopped, because there are so many ways that it can do that. There's so much untapped potential, just limited by the creativity of designers, and dealing with power dissipation levels of software and architectural issues if we can't do it at a hardware level. So I think there are some real questions to think about. So one question is technology has been the key driver here. But we have created this enormously powerful technology base. Incredible things can be done with it. Will technology drive 21st century electronics? Okay. Not everybody thinks so. So here's an article from New York Times talking about Apple's philosophy. So what they're saying is, hardware offers only fleeting advantages. From their point of view, all of their competitors are going to have the same hardware almost as soon as they do. You can't gain any competitive advantage with new hardware. So they're saying where you gain the advantage is in software and in product design, because those things are more difficult to replicate. You can keep those to yourself. Is that true? We hope not, if those of us that are involved in technology. Here's a different perspective. This is Dennis Buss. So Dennis was chief scientist at Texas Instruments for a long time. He's given this talk at a few places. What he sees is something he calls the era of accelerated technology innovation. So he has a completely different view of what the future will be. So his view of the world is that, yes, everyone will have the same hardware. The hardware won't give you any advantage over your competitors. But what can give you an advantage is differentiated technology. What can you add to a basic CMOS platform that everybody else has that will do something special and give you a competitive advantage? So that means that the technology development could become more and more interesting because it will be very diverse. You're going to get all of your computation and communication on your basic CMOS platform, and then you're going to add to it some special capabilities for sensing or whatever. So it will be more diverse. It'll be less predictable. It'll be harder to have 20-year roadmaps for what should be done because you're going to be driven by what special opportunity can this new device enable for you, driven by needs. So all kinds of really exciting things are happening. So here's an example. I think I heard a number last week. Something like $3 trillion has been invested to get silicon technology where it is today. Another thing to think about is how can you leverage that $3 trillion investment? What more can you get out of it? And there's an awful lot more that you can get out of it. So here's one example. So this is gene sequencing, where this company Ion Torrent, we heard We heard this fellow talk at the Electron Devices meeting last week, how they took, I think this is 180 nanometer CMOS technology, not state of the art. They married it with ion-sensitive FETs, 1970, were developed in the 1970s. They put the two together to dramatically lower the cost of doing DNA sequencing, leveraging that enormous investment in silicon technology to do something that was the people who developed that technology never had in mind. How many other opportunities are there out there? So John Rogers his group is doing a lot of interesting things. So he's also doing a lot to leverage silicon. So this is an example of, you make silicon thin enough, it's flexible. You etch it in the right way so that it will buckle up and it can be stretchable. So this is an example of an electronic circuit that is flexible and stretchable, and you can wrap around the heart muscle to monitor the electrical activity of the heart, or you can make it into a balloon, insert it in the heart, blow it up, and you can monitor things from the inside. There's an article in the New Yorker that came out just recently talking about the body electric, and it's all about what the Rogers group is doing with silicon like this. And it sounds like science fiction. These are some of the things that are going to happen, whether we have a new digital switch for computation or not. It's just amazing. So if you look to the future, I've been involved in lots of these rump sessions and discussions, and we've never been very good at this, and I'm probably no better than anyone else, but you have to think about it, right? Because you have to think about what you should be doing. So we have this technology. So one of the things we're going to do, when scaling ends, and it will end sometime before I retire. So now I can't retire until. But when it does end, there are other ways to extend the technology. There'll be some 3D that'll come along. There'll be special purpose devices that maybe do the core functions at lower power, that maybe do image recognition in a way better than CMOS. There will be ways that we can extend the capability, and the underlying platform will just get more and more powerful. And there'll be more and more incredible leverage that can come. That's going to happen for sure. And that'll happen for a long time. And then there's Dennis Buss's vision. There will be companies that will learn how to, if we could add some special technology to that CMOS platform, we could do something that our competitors can't, because we've got a technology that is not widely available. That's this era of accelerated technology innovation that he talks about. And then there are others. There are completely new technologies. Maybe quantum computing is one of these, where you'll develop a whole new technology that can be leveraged in different ways. And well, one of these, I think you can say with certainty that this is going to happen, and that silicon is going to be the dominant technology, showing few signs of slowing down, probably through the middle of the 21st century. What else will happen? A lot of it is up to what we make happen. So one of the things that's happening, and this came from an NSF panel that I spent about 2 years on here recently, is you're seeing a lot more convergence between nanotechnology and nanoelectronics and other fields. It's always been closely aligned to information technology. More and more it's getting closely connected to biology. There are just huge applications there. And more to cognitive science. So more and more talk about human-computer interface. So what this is going to mean for those of us who develop technology or to develop tools for modeling and simulating technologies is that it's not just going to proceed straight by thinking about, well, what problems do I need to solve? What problems do I need to solve so that I can address the problem we've been addressing better? It's going to be shaped more and more by its interactions with other fields. So in thinking about, what new capabilities do we need? Yes, we need to improve the capabilities that we have, but maybe we need different kinds of tools that help us couple to biology in different ways. Maybe we need to put tools from different domains together. Okay, so maybe we need not only to make the tools that we have better, but maybe we need new kinds of tools to make these things happen. And it also helps you think about what are we doing when we're educating PhDs? What should a PhD be in this new era of electronics? One of the things I think we're going to need more of is something you'd call a technology maestro. That more and more solving electronics is going to be driven probably by solving important problems. And solving important problems means putting together different technologies. So electronics will have a role in almost every challenge that we face, but you'll be working very closely with biological systems, human cognition, energy, environment security. So in order to contribute to that, you have to be very deep in your field. And we've been good at educating people who are very deep in their field. But we're going to have students and working engineers and researchers who understand related technologies and disciplines. And we're going to have to be able to teach our students how to be able to learn and adapt and innovate and do that quickly. Because we're not going to have 40 years of perfecting one technology. We're going to be putting many different things together in many different ways. So I'll end just by saying a couple of the things that I'm involved in recently here, thinking about how do we get ready for this future. So one was that 50 years ago, there were a group of very bright people who realized what the future was and reoriented engineering education so that we could produce engineers that were prepared to take advantage of that future. So we've been doing, our little project these days is called NanoHub U. It has a similar philosophy. It's to try to bring in the things that we're learning from research on nanotechnology, these new ideas and approaches into the engineering curriculum because they're going to be important for electronics in the future. This is what the website looks like. So if you haven't seen it, go to nanohub.org/u, and you'll see a series of short courses. So the idea here is a set of 5-week courses on a wide variety of topics. The philosophy is to make these courses available to anyone who has a bachelor's degree in any field of the physical sciences or engineering. You don't need a long string of prerequisites. The one that just finished last week was a short course on electronic biosensors. There's one starting in February, I believe, on bioelectronics. So it's for people who don't have a biology background, that realize that many of the electronics applications are going to involve connections with biology. And how do you learn those? So we're having a lot of fun with that. We got it started at Purdue. We're hoping to expand it to faculty and other programs outside of Purdue. So another effort that I'm involved in here is something called NEEDS. So NEEDS is an NSF-funded initiative, and NEEDS is about two or three slides, just wrapping up. So NEEDS is a project, we're just starting our second year. It's funded by the National Science Foundation. The first 10, 12, 15 years of the National Nanotechnology Initiative were heavily focused on materials and devices, physics and chemistry and material science. What NEEDS is about is to try to move that work towards applications. So if you work in this field, very often you're doing what I described. You're trying to develop a simple analytical description of the device that you're working on to guide your work. If you augment that by the other capabilities that circuit designers need to work in a SPICE environment, then you have a tool where designers and application people can use to explore potential applications. And then you can make connections to the circuits and systems community. So really this effort is to try to connect people who work at the basic technology level better to applications and circuits level, which are really more and more, I think, going to be driving where we go in these new worlds. So we have a mission to develop SPICE-compatible physics models, but we think more important than that, than developing a set of models, because in the limited time that we have, we're not going to be able to develop every model that's needed. We might not even develop the ones that are most important for the future. So more importantly, we're trying to create a complete environment, the processes and platform for developing compact models and help make this connection. So if you go to this website, this is what you'll see. You'll see some models, just a few now, but more and more that are being deployed. Something very important is you'll see a MATLAB-based compact model development platform being developed by my colleague Jayjeet Rai Chaudhary. And I was surprised to see Jayjeet in the audience. So if you're interested in that, have a look at the webpage to see what this is all about. But what this is a MATLAB-based environment that will help you develop circuit models in a familiar environment to most of us who work in this field, and then even to test that in a circuit environment, in a SPICE-based MATLAB engine to do DC, AC, and transients. Much of the work that we do can probably be done entirely in that MATLAB environment. Okay, so I'll just conclude. What's happened in the last 50 years has been really amazing. And you can find all kinds of, I think we all agree that. This was a series on public television about the transistor, calls it probably the most important invention of the 20th century. I was at a meeting a year ago with George Whiteside. This is what he has to say about what we've witnessed. Probably one of the most amazing things that humankind has ever done. It's almost impossible to overstate the significance of what's been accomplished. Things like this happen once every 1,000 years or so. Maybe Isaac Asimov did go a little bit over the top. Here's his quote about the planar process that makes integrated circuit processing. I might not go that far, but it really was significant. So what's my own particular take? 10 years ago, I wrote this perspective for science, and the title was Moore's Law Forever. And I just went back and looked at this to see what I had to say. All right. And actually, what I had to say is not too bad. So Moore's Law is really, if you think about it, as what's made electronics progress is that by shrinking devices, we've been able to lower the cost per function and put more and more in a product. That continues to happen at a breathtaking pace. It's fast. It's hard even to keep up with it. But we're going to reach the limit of scaling. I don't know if it will be 10 years, or 12 years, or 15 years, but it's coming. But that doesn't mean that progress will stop. There are other ways to continue progress going, and there's simply too much at stake not to let that happen. So, in that sense, progress in electronics isn't going to stop when scaling stops. So, I said that 10 years ago. I'd probably say exactly the same thing today. But 10 years from now, it'll have to be a little different. But 10 years from now, we'll be virtually at the end of scaling, and it will be all about continuing it by other means. So, my own belief, history says that we should be optimistic in this. This is amazing. The last 50 years has been unbelievable in terms of the technology. I think the next 50 years are going to be just as amazing. And I'm only talking about silicon-based electronics. What's going to continue to happen there for the first half of the 21st century is just going to make what we've seen. What we're seeing here now will seem like that 5-micron NMOS process I showed you at the beginning. It'll look like crude technology. That's going to happen. Okay, so I hope maybe I've stimulated some discussion or thinking or debate, and if I've got this all wrong, please tell me. I'd be happy to chat with you about it. All right, thank you.
Take a break, or we must have some questions.
Disagree.
Students? So what do you see as a new switch?
What do I think? That's a big. One of the things I think we've appreciated in the search for the new switch is just how hard it is to replace a CMOS transistor. So we've been looking for probably a decade now, really, well, maybe more than a decade if you go back in electronics, as something to replace the CMOS transistor. There is just nothing that we've come up with that can replace that. You can find some switches that will do better for certain applications. I think we're going to start to see complementing the basic CMOS platform with some special purpose functionality, special purpose switches that might work in really low power environments, for example. But nothing I see says that we're going to replace the CMOS transistor.
I like this one. You mentioned that the world has invested $3 trillion into the silicon technology.
Yeah.
That probably also include all the designs. Yeah. That's very huge amount of initiative to change the the design, the standard microprocessors, and the software on top of it.
Yeah.
Right. That's why you don't want to change it. Once you change the lowest layer by changing the class, affects everything involved.
Yeah, that is a really important point that is often not well appreciated. Now, I saw some numbers a few years ago saying something like, if you look at the cost of a chip, I think something like 10 to 15% of it is in the manufacturing cost. And lumped into that is all of the R&D that went into the process development and everything. That means like 85% of it is in the design. So, when my colleagues on the design side, when we talk to them about coming up with a new switching device, they'd say, fine, as long as you can plug it into my design environment. Because that's much more expensive than, we talk about these billion-dollar fabs. The design environment that's been built up over this period to produce these things is much more significant.
So last question. Okay. So
There you go.
Oh, I thought it wasn't last. Okay. It's not really a question. It's just to pick up on the comment that you made right at the end about the bio and the cognitive things coming in as well, and it ties a little bit your talk with Gabriel's beforehand. There's some assumptions that have gone into your talk and the development of CMOS and all of these things, which are basically the binary system, the idea that you have ones and zeros and that they're sacred. And what Gabriel was trying to say was that there are other ways and so forth. But there is a sort of way that you can think about that as information technology, which is that as hard disks in particular have got smaller and smaller, the need for error correction has just grown and taken over. But that can go further and further, and you can get to the point that you give up your CMOS and just go to some input-output response of some kind in a circuit and do everything through clever software and so forth. I don't know if that should be included as, that's the way biological systems work, for example. They're not precise, they're actually rather random, but they're very, because of the global sort of structure of the thing, they are precise in the end. And that's where the cognitive word comes in a little bit, and I don't know whether there's a big future in that or not, but it's really just a comment.
And I agree, there's enormous opportunities there. There's all kinds of areas like that we need to explore. And it's hard to predict where it will go.
Okay, it's really time, and because we have to reconvene at 2 o'clock, so let's thank our speakers again. And, we will meet here again